So let's think about what it would take to actually derive this relationship between temperature gradient and thickness and geostrophic wind. Well, if we're going to be talking about the rate of change of the geostrophic wind in the vertical direction, we're probably going to need to start with expressions for the geostrophic wind itself, which I just took from an earlier chapter. You've memorized these definitions already for the zonal and meridional components of the geostrophic wind. So, and notice I have them just in forms of the geopotential on the right-hand side. All right. Now, another form that we're working with here, it can be shown that through the ideal gas law and hydrostatic balance that this identity here is true, that the part here that's relevant to what we're going to be doing right now is the part on the far left here. This change, we're going to keep seeing terms that have this partial phi, partial p, where there's change in geopotential with respect to pressure, and we're going to make this substitution. Okay, so you're going to see this a couple times I think twice actually in the next couple slides here for their derivation. Now, what we're going to do is we're going to, it says take the derivative of these terms right here and with respect to p, and then we're going to see if we can make some substitutions to get this in terms of change in the geostrophic wind with respect to height. So what we're going to do is we're going to start with the geostrophic wind in the zonal direction. And we're going to just take the derivative of both sides with respect to pressure. So you can see on both sides that it took partial p. Now on the right-hand side over there, we can actually change the order of these derivatives. You can almost always do that, where you change from like partial p of partial y. You can almost always change them around. In fact, I think you maybe always can, as long as it's a well-behaved field. You can change it to partial y, partial p, just changing the order of those derivatives. And then we do that substitution that I mentioned a few slides ago. Take that partial phi, partial p, and put in there negative RT over p. That's pretty straightforward. I hate equations that have a negative of a negative in there. Let's go ahead and cancel those negatives out right away. That just seems like the simpler. Now I'm going to take this equation here that's at the bottom of the slide. I'm just going to move it up to the top because I couldn't get this all on at one time. And what I'm going to do here is I'm going to take the terms out of that partial derivative that are constants. R is the gas constant, that's no problem. And now P, because we're working on an isobaric surfaces, is a constant, so that can come out of the derivative too. And we just are left with partial T, partial Y. Now we can move that P to the left-hand side of the equation by multiplying through by P. And then there's a little substitution here that comes to us from calculus, where you could like take P over partial P becomes 1 over partial log P. Whether that's something you keep on the tip of your tongue or not is not terribly important. But hold that thought. We now have a form of the equation here that has the change of the geostrophic wind's U component with respect to height, well, log P, is a bunch of stuff on the right-hand side that's pretty straightforward. Hold that thought. Let's do the same basic derivation except for the meridional component of the wind. And I do see that I made a mistake here on that arrow there. It should say start with the geostrophic wind in the meridional direction. But we're going to do exactly the same steps here. We're going to take the derivative with respect to pressure. And then we're going to rearrange the orders of those derivatives on the right-hand side. And then we're going to do that substitution that I mentioned earlier where we get rid of partial phi, partial p, and replace it with RT over p. And let's move that negative sign out in front. It's just a tidier equation. Now, again, I'm going to take this equation that's at the bottom of the screen right here, and I'm just going to pull it up to the top of the screen to make more room. Okay, I'm going to move the things that are inside of that partial x that are constants. I'm going to move them out of the derivative, leaving me with just partial t, partial x, the temperature gradient in the x direction. And I'm going to move that p to the other side of to the left-hand side of the equation by multiplying by p. And then again, this is that same substitution from calculus where we took p over dp and changed that to 1 over partial log p. That's just a little substitution from calc. If you don't remember it, it's not the end of the world. And we have another form of the equation here. And again, hold this equation in your mind because we've got a change in the geostrophic wind with respect to pressure.